Hi everyone, I hope you're doing well. I'm just going to horse through the mini mock questions. So I'm going to start with the ordinary level and go to the higher level after that. Make sure you've had a try at these questions before watching this video, okay? It's pointless otherwise. Make sure you've had a go and that way just refresh yourself about what the questions were like because it's been a couple of weeks and for it to be useful, you kind of need to have had to go yourself recently, okay? Now I'm going to go for speed here, so make sure you have a look at the questions, have them in front of you. We'll go for the ordinary level question 1. It was forces, sort of a force revision exercise. So Sir Isaac Newton was an English mathematician, blah, 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 blah. Okay, a block weighs 400 newtons, so that's its weight. A crane lifts the block so that it moves upwards with constant velocity. Okay, so if it's using constant velocity, it's not accelerating. It's moving, but it's not accelerating. That tells us that the forces are balanced, that whatever force is pulling it up is also 400 newtons, because you have, according to Newton's first law, and a body will stay at rest until an external force acts upon it, and then it will accelerate. And if the forces are balanced, it will either stay in a state of rest or move at constant speed. So for that one, the number they were looking for is 400 newtons, because the block is moving upwards, I beg your pardon, at a constant speed. Newton's second law of motion states that the force on an object is proportional to its rate of change of momentum. Calculate the resultant net force on a 9 kilogram object in the diagram above. Well, you've got 8 newtons pulling it to the right, 6 newtons pulling it to the left. So overall, 8 versus 6, you've got a winning team here of 2 newtons pulling it to the right. You have to indicate the direction as well here, okay? Because remember, it's a vector, not a scalar. It has a direction as well. So calculate the resultant net force, 2 newtons to the right. Oh, they structure the question like there. In what direction does it act? So even if you missed it, you could read the question really carefully and then specify to the right. Calculate the acceleration of the 9 kilogram object. Well, a special case of Newton's second law is that F equals ma. We're looking for the acceleration. So let's rearrange this, bring the m across. So the force divided by the mass will give us the acceleration. We have a 9 kilogram object, so that's our mass. We have a force of 2 newtons. So the acceleration is going to be 2 over 9 meters per second squared. Here's me being lazy. Do it. 2 divided by 9 equals. So your calculator will leave it as a fraction. Press the ST button there, and it is 0.2 recurring. So 0.2 recurring meters per second squared. Make sure you include the unit or thrown away marks. State Newton's third law of motion. Okay, so we can go with the colloquial version, which is for every action there's an equal and opposite reaction. And just to be a bit more exact to make sure you get the marks, if body A exerts a force on body B will exert a force on body A equal in magnitude but opposite in direction. A little diagram sometimes will help there. So when two objects or two things exert a force on each other, it's always equal in magnitude and opposite in direction. Use Newton's third law to explain how a rocket takes off. A label diagram may help in your answer. Okay, so let's have a little rocket. Now, a lot of people have a good stab at this, but let's think about when the rocket is in motion, not so much when it's off the ground. So let's say the ground is miles away, and the rocket is still moving forward. Now, the reason this is happening is the rocket will exert a force expelling the gas, and the gas will exert a force on the rocket as well. So the rocket will exert a force on the column of gas that it's ejecting, and that gas will also exert a force on the rocket, pushing it up. Okay, I might just switch to using an actual bit of clean paper here for this. A car of mass 700 kgs is at rest. Okay, now a couple of things to do here. One is do a diagram. Make sure it's a little bit clearer to hear what's happening. So, cartoon car here, 700 kgs. Its initial velocity is 0. So let's zoom at this just in case we have to zoom out in a minute. So the initial velocity, we're told it's at rest. Now that's where they're hiding information in plain sight. That's telling us that its initial velocity is 0 meters per second. It accelerates at a constant rate, a constant rate for 6 seconds. So the time it accelerates for is 6 seconds until its final velocity, Mr. Bond, is 18 meters per second. Okay, so let's see what we need to do. Calculate the kinetic energy of the car when it is traveling at 18 meters per second. Okay, well first off, here's where I go to the list of formulae that we were given. Now remember, on the day you'll have these in your logbook, and you have to be familiar with finding them quickly. So we're probably going to start using the logbooks more than these cheat sheet kind of things. to make sure you're getting more fluid to find them. But in any case, kinetic energy there is half mv squared. So just plug in the numbers. We have a mass of 700 kgs. Its velocity that we're looking for is 18 meters per second. And we just have to square that. So we have 700 times 18 to be squared. Gives me a kinetic energy of 226,800. And don't forget your units. Anytime you're talking about energy, that unit is going to be joules. Okay, calculate the acceleration of the car. Now again, we're going to need a little bit of help on this. Let's go with v equals u plus at, one of the first of our universal standard motion equations. So we're looking for a, so we might do a little bit of rearranging here, but we do know v, u, and t. So we have our three things, and maybe I'm just skipping forward a little bit too fast here. Considering that these are the tools available to us, some of them are going to be useful and some of them aren't. Anything with an s for displacement, unless we've got all the other quantities, it's not going to be that useful to us, and we're not looking for displacement. So I go with this one here, v equals u plus at. Let's rearrange it to get t on its own. So bring the u across. V minus u is equal to at. And we're looking for acceleration, and that acceleration is v minus u over t. Just the standard classic definition of acceleration, change in velocity over time. So v minus u, that's 18 meters per second minus 0 meters per second, because it was at rest, all divided by the time of 6 seconds. And that gives us 3, and they're looking for accelerations, meters per second squared, or, s to the minus 1 divided by another s, gives us the m, s to the minus 2. So there's the acceleration of the car. Now, a little bit trickier, calculate the net force on the car as it accelerates. Okay, so let's think this through for a minute. So we have the acceleration. We just figured out the acceleration is 3 meters per second squared. So the net force on the car. So the net force is just the force that's causing it to accelerate. So what force will give us an acceleration of 3 meters per second squared? Well, F equals ma. So that force is equal to our mass of 700 kgs times our 3 meters per second, which is 2100 or 2100. And here we're talking about force, so it's newtons. Okay, we're getting there. Last couple of parts now. Part 9. Calculate the friction acting on the car if the engine provides 3000 newtons. Okay, a bit tricky here, because if you think about what's happening. So the engine is supplying a forward motion of 3000 newtons. But we're only experiencing 2100 of this, because friction has taken away some of the force, as opposed to so much. So the engine is providing 3000 newtons of force, but the missing 900 is caused by friction. Force of friction is 900 newtons. And final part, state one method of, I'm going to be a little bit slapdash here, I should really spell it out. So let's go with the total sum of forces there is the force from the engine plus the force from the friction is equal to the net force. So we know that the net force was 2100, the force from the engine was 3000. So the force of friction is 2100 minus 3000, so that's minus 900, so it's slowing it down, so it's minus 900 newtons. Okay, one method of reducing friction, anything involving lubricating moving parts will do the job, or in terms of a car, you could have better tires, to reduce friction, I beg your pardon, you could have a smoother surface lubrication, they both do the job. Okay, so that's the first question. Bit of a beast. I'll keep moving. I'm going to try and do this all in one take, so if there's a couple of mistakes in here, it is what it is. Alright, so the normal human body temperature is 37 degrees Celsius. The temperature increases when the person's fighting infection. The thermometer in the photograph on the far right measures infrared radiation emitted from somebody's forehead. Heat may be transferred by radiation and conduction. Name the other way in which heat may be transferred. Well, remember that CCR. Great band. Conduction, convection, radiation. So the one they haven't mentioned there is convection. Distinguish between heat and temperature. Well, heat is a form of energy measured in joules. Or a measure of something's total internal net energy. And temperature is a measure of something's hotness, which is not the same as how much heat it has. It's a measure of the hotness or coldness of a body. Now, if my handwriting here is a little bit dodgy, remember you've got all of this in that handout of notes, so they got a more precise definition. But that's really what they're looking for there. Heat is a form of energy, temperature is a measure of hotness. Convert the normal human body temperature from degrees Celsius into degrees Kelvin. You've got to be careful here, guys, okay? Because looking at this is the way the formula is given to you in the logbooks. So the temperature in Celsius is equal to the temperature in Kelvin minus 273.15. So the temperature in Celsius here is 37 degrees, but we're looking for it in Kelvin. So we're looking for the Kelvin. So we need to rearrange it first. So bring the 273 across. So the temperature we're looking for is whatever the temperature is in Celsius plus 273.15 will give us our value in Kelvin. A lot of people, you might get very easy to get mixed up on this and end up, subtracting the 273.15. So the number we're looking for here, and that's not a 0, it's a theta. So the number we're looking for here is 37 plus 273.15. And that should be 310.15. Did I manage to mess that up? Nope, we're good. So that's 355 Kelvin. Don't forget the OD unit. Okay. Thermometers are designed to make use of thermometric properties. What is a thermometric property? It's any property that increases measurably with temperature. So it's a property that increases measurably or proportionally, or varies is probably a better word, a property that varies measurably with temperature. Now again, remember, if you feel like I'm skipping over this definition, they're all in a handout, okay? But that's the core of it, that's what we're looking for there. State one example of a thermometric property. Okay, there's loads, so you could go with the length of a column of liquid. That's our traditional thermometer. You could go with the EMF of a thermocouple, the electromotive force of a thermocouple. You could go with pressure constant volume, or volume and constant pressure. Or you could go with the colour. There's quite a few examples there. I'm sure I missed out on one or two, but any one of those would have gotten the marks there. So that's the first part. We're half of the question, 28 out of 56. The second half, a bit more mathsy. Just be a little bit careful here because it's not very tricky, but they do throw a couple of curveballs at you. So let's look. The solar constant is a measure of how much radiation from the sun falls on each square meter of the Earth's surface in 1 second. It has a value of 1.36 kilowatts per meter squared. Let's just look at that unit for a minute. That means that every second, 1.36 kilojoules will fall. I think that's going to be one of the questions they ask here. That means every second, 1 meter squared of the Earth's surface will get 1.36 kilojoules of energy. And let's just get rid of that kilo because that's going to trip us up later on. That's equal to 1360 joules per second, because that's what a watt is per meter squared. Okay, but we're getting ahead of ourselves, sorry. So, first question. Calculate the area of the garden. 6 by 9, 54 meters squared. 6 meters by 9 meters, the area of the garden. And I'm being a bit of a bad example here. I should be labeling this. This is part VII. If they're kind enough to label the questions, we should be kind enough to label the answers. It makes the examiner find your work easily. Okay, calculate how many seconds there are in 12 hours. Okay, well, 12 hours. Let's figure out how many seconds are in 1 hour first. So every hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. So if you want to find out how many seconds there are in 12 hours, it's 12 times 60 minutes in an hour times 60 seconds in a minute. And oh, no, syntax error, not the answer, please. 12 times 60 times 60. 43200. 43200 seconds in 12 hours. So that was part VII, Captain. Calculate how much energy will fall on the garden in 12 hours. I'm going to slow down a little here. So we know that every second, 1,360 joules will fall on the garden. Will fall on an area of 1 meter squared. This garden is 54 meters squared. That's the area. And the time they're looking for is that 12 hours, which is equal to 43,200 seconds. So overall, if 1 meter squared will get that energy in 1 second, 54 meters squared of that over a longer time, we just multiply all our answers together here. So our 1360 times 54 times 43200, it's going to be quite a big number, I think, times 54 times 1360. So I got a final answer here of 317,260,8000, and that's joules, because remember all our other units have taken care of themselves by multiplying them out. We just end up with joules. And if you're in any doubt as to the units, just check back on the question, how much energy will fall? So energy, joules. Now you can leave your answer in numeric form, or you could write it in scientific notation, 3.17268, whatever, and then how many times we have to hop the decimal? 1, 2, 3, 4, 5, 6, 7, 8, 9. So by 10 to the power 9. Quite a lot of energy. Excuse me. Okay, last couple of parts of this question. Heat is transferred at different rates depending on the material it is moving through. Describe an experiment to compare the rate of conduction through different solids. Okay, a diagram helps you out massively here. So there's two ones that could do the job. One is where you have a small candle, and over it you have one of those rings with the 4 types of metal sticking in from the outside: brass, copper, iron, and something else. And on each one we have a thumbtack secured with a little bit of petroleum jelly, like Vaseline. And the candle in the middle heats up the metal. Conduction will pass the heat from particle to particle, and it will cause the Vaseline to melt and cause the pin to drop. And then the one that the pin drops from first is the best conductor. Now, to get the marks for this, you have to draw the experiment, label everything, which I've not done because I'm going for speed here, but label everything, and also describe what you'd observe. So really, they're looking for 3 things here: the setup, how you do it, and what you see. The other one, which I saw a few people using, which is excellent because it shows you've been doing the study, is the one with, and we didn't do this in class because we don't have one of these setups, but you've got a trough of water with the 4 metals sticking out, and the water is heated. And again, same kind of vibe. You've got a little a thumbtack on each end, and the first one that drops off. Whatever way about starting the heat going, it's how quickly it gets conducted along the metal, and the first one to drop the pin is the best conductor. Okay, final bit. U value is a measure of the rate of heat loss through walls and windows. Describe 2 ways of reducing heat loss from a building. Well, more insulation is a great one. Adding more insulation to your walls or ceilings. Maybe double glazing windows. Double glazing. That's probably most of it, really, isn't it? Insulation and double glazing. I'm sure there's another one that I can't think of at the moment. Those are the 2 biggies. Getting more insulation on your house, double glazing, and maybe things like closing all the windows, not opening doors for long periods of time, draft excluders, those little furry rug yolks you put along the bottom of your doors. Draft excluders are another one. Okay, I'm going to keep cracking on. Question 3 is the calculation one. The diagram shows a water boiler which is filled with 0.7 kgs of water. Okay, I'm going to start just noting down the important numbers. These kind of calculation questions, very, very easy to get mixed up on what's happening. So I always draw it out, So the mass of water that we're dealing with here is 0.7 kgs. Its initial temperature, its initial temperature is 20 degrees Celsius, and the boiler has a power rating of 3 kilowatts. Now that kilowatts, that's going to annoy me later on, so I'm just going to convert that into watts. 3 kilowatts is 3,000 watts. Or if you're more comfortable, 3 by 10 to the 3 watts. They're all the same, they're all equivalent. Calculate the energy needed to raise the temperature of the water from 20 to 90 degrees Celsius. Now again, I don't expect you to remember all these formulae. That's why we have the book. So the energy needed to change something's temperature is the mass times the heat capacity times the change in temperature. So for us, let's just write out the formula first. That shows the examiner you know what you're doing, and even if you make a small mistake in your calculations, you still get most of the marks. So the change in energy is the mass of 0.7 kgs. I'll leave out the units for now, and I'll just put them in at the end. Times the heat capacity of water, which is 4,200 joules per kilogram per Kelvin. I've just gotten that from the question here. And the change in temperature, now, you don't have to worry about converting it into Kelvin, because when you get the difference in temperature, 1 degree of difference in Celsius is equal to 1 difference in Kelvin. One, not to say that Celsius is equal to Kelvin, but when you're talking about the difference, if you drop by 20 degrees Celsius, you also drop by 20 Kelvin. So anyway, it's gone from 20 to 90. So the energy change here is 70 Kelvin. I'll leave out the units. Now it's just a matter of finding out how much energy that would take. So 0.7 kgs times 4200 joules per kilogram per Kelvin times that Kelvin change of 70 gives me the amount of energy we need is 205,800. And again, energy, always joules. Okay, part 3. Calculate how long it will take the boiler. Sorry, I beg your pardon. How many joules of energy are supplied per second by the boiler? So that's part 1 we've just done. Part 2, well, we know that the boiler has a power rating of 3,000 watts, which means 3,000 joules will be transferred every second. My handwriting's getting worse as this goes on. Okay, part 3. So, how long will it take this boiler to heat the water to 90 degrees Celsius? Well, we know the energy we need is 205,800, and the amount it can supply per second is 3,000. So, to find out how long it will take, you take your total energy that you need and divide it by the rate of transfer, the 3,000 joules per second. So, we've already got our 250,800 in the calculator. Divide that by 3,000, and it gives me 68.6, and that is seconds, because the joules will cancel off with joules. Second minus 1 divided in just become positive, just become seconds. Okay. Has my, oh, you piece of rubbish. No, you're not a piece of rubbish. Sorry guys, I'm talking to my computer. I thought it had turned off. It seems to still be recording, so I'm going to crack on. I thought it had turned off and I'd have to start from the start. Alright, sorry about that folks. Skip forward past that. So that's part 3. How long will it take? 68.6 seconds. Now that seems quite fast to heat that water up. Let me just check our numbers here. Sorry for the confusion there. 0.7 times 4200 times 70. 205,800 divided by our power transfer of 3,000. No, that's what we got. 68.6 seconds. That seems quite fast, but then it is quite a powerful boiler. Okay, last part. Part 4. Where should the manufacturer place the heating element of the boiler? Always at the bottom. Now, the reason he placed it at the bottom. First off, a lot of people had a good stab at this and they said something like heat rises, some version of that, which is true. But really, to be a bit more specific here, it's because it'll heat the colder water at the bottom, which is denser. This is all down to convection currents. So what happens is your heating element at the bottom of your kettle will heat the water that's nearest to it. And what happens is when you heat water, it expands. It takes up a larger volume, which means it's less dense. And less dense things go up. And then the denser, colder water at the top will drop down to fall its place and get heated. So if you want to heat the water thoroughly, have the heating element at the bottom, as opposed to, if you had it at the top, you'd have your colder, dense water down here, which is never going to be in contact. So most of the thermal transfer will happen up here. And get like really boiling hot water at the top, but very cold water underneath, which is not ideal. Okay, that's the heat capacity question. The sound one we've done in class, but you know what, for the sake of being complete, in case anyone wasn't in it, we may as well horse through it. So when a person sings, their vocal cords vibrate. These vibrations travel the air through the air to the listener's ears. Sound is an example of a mechanical wave which therefore needs a medium to travel through. Describe an experiment to show how sound is a mechanical wave. Now when they say describe, you don't have to do a massive diagram on this. You don't have to do, like an experimental question where you lay out all the design and do loads of calculations. It's just a very quick explanation. Now this is one of those ones that I remember I described in class that we didn't actually get to do. We did get to discuss. It's where you've got a big jar, a bell jar, attached to a vacuum pump which will suck out the air. And inside you have a bell ringing, and what happens is as you pump out the air, the volume of the sound from the bell will get quieter and quieter and quieter because there's no air for the medium to travel, for the sound to travel through. Sound is also an example of a longitudinal wave. What is a longitudinal wave? Well, a longitudinal wave is one in which the vibration or the oscillation is in the same direction as the direction of movement. It's the same direction that the wave is traveling. So let's just look at that in a little bit more detail. So you've got your particles of sound, or your particles of air, and when sound passes through, what happens is this particle will vibrate back and forth in that direction, then we'll pass the sound on the energy onto this particle, which will vibrate back and forth, which will pass this one to go back and forth, back and forth, back and forth. The wave is traveling in this direction, and the particles are vibrating in the same direction, as opposed to the other type, which is transverse, which is when the waves are traveling in that direction and they vibrate at 90 degrees. The traditional wave, the sine wave. Okay, part 3. Sound waves can undergo reflection, refraction, diffraction, and interference. A doorway may cause a sound wave to diffract, but it will not cause a light wave to do so. Explain why. Well, that's because the gap has to be of a similar size. So the size of the gap has to be a similar size to the wavelength of the wave. And sound has a long wavelength that's pretty much similar to the size of the gap of a door. Whereas light has really tiny wavelengths. It's like in the order of the minus 14 or 13 or 12, really, really tiny wavelengths, which aren't, so that the size of that gap is too big and you won't get much diffraction happening. Sorry, putting in the numbers there, you didn't really need that. You just need to say that the wavelength of light is far too small for diffraction to happen because the gap is so much bigger in comparison. Describe an experiment to show that sound waves undergo interference. This is the one we did where we had the tuning fork, and you hit it, and then you hold it up to your ear, and you turn it in place, and then the waves being produced by one of the halves of the tuning fork will combine with the waves being produced by the other, and you get this point where as you rotate it, it'll get loud, and then it will get quiet, and then it will get loud, and then it will get quiet. That's one way. Another way, we haven't done this in class because our speaker setup isn't really good enough. If you have two speakers emitting coherent patterns of sound, so the same wavelength, the same frequency, and in phase, then as you walk from left to right along between these two speakers, you get again that kind of loud, quiet, as the waves interfere constructively and destructively with each other. So either of those experiments will do the job. I'm going really fast here, guys. That's why I'm not labeling every diagram, but then again, we're just going to make sure this makes sense to you. Okay, final part. Sound waves do not undergo polarization, but light waves do. What is meant by polarization? Well, polarization is when you make a transverse wave vibrate in one plane only. So the analogy we'd use for that, this isn't to describe an experiment or anything, but the way to show it, imagine you've got like a slot in a box of cardboard, you're sending a wave towards it, it's vibrating in all directions, it's vibrating like that, and it's also vibrating like that, but only one plane will pass through, so that wave is then polarized. But you can't do that with sound waves because, remember we said they're vibrating in the same direction, so they'll just like wobble back and forth as they go through. So they're not polarized at all. Okay, final part of the ordinary level question, and I might stop the video then and separate these into higher level one, so I can gather my thoughts and not make you sit through all of this. Or twice the length that you need to do. Okay, a student carried out an experiment to measure the specific latent heat of fusion of ice. During the experiment, ice at 0 degrees Celsius was added to a calorimeter containing warm water. Draw a labelled diagram of the apparatus used in this experiment. Okay, well you've got your calorimeter of water. Label it. You have some water inside. I'm doing terrible diagrams here. We have some ice that we're going to put in. You obviously would have much more, take your time on the day. Don't be rushing like this. And use a pencil. If you make an error, you can cross it out. Use a ruler. Label everything. And what are we missing here? We need a thermometer. We need something to measure the temperature of all this. So flash thermometer in there. And we also need a mass balance so we can calculate the mass of everything involved. It's a terrible diagram. I don't know what this would be. Mass balance. As long as you label it, we're happy out. Okay, label diagram. So we've got our calorimeter, we've got our water, we've got our thermometer, we've got our ice, and we've got our mass balance. I think that's everything we need. Okay, the ice was crushed before it was added to the water. Why was the ice crushed? Well, when you crush up the ice, you break it into smaller chunks, and that increases the surface area, which causes it to melt faster. So the ice was crushed so that it will melt more quickly due to the surface area being more exposed. Melt more quickly. Mass and temperature were measured in this experiment. Name one mass measured and one temperature measured. Well, you could measure the mass of the ice, or the mass of the warm water, or the mass of the calorimeter. And for the temperature, you could measure the temperature of the water. Really, that's all we're measuring here, because we know the ice is at 0 degrees Celsius. Name an instrument used to measure one of the quantities listed in the question above. So that's either a thermometer to measure temperature, or a mass balance to measure mass. And finally, state one precaution used in this experiment other than crushing the ice. Now, when they say precaution, they're not talking about safety. I mean, obviously you have to be safe, but they're talking more about getting an exact result here. They're talking about being a bit more exact in our experiment. So one precaution used other than crushing the ice, well, we dry it. We dry the ice first so that there's no little blobs of water on there that will affect our results. We're very careful when we take all our measurements. We don't splash any water, so we try to be gentle not to spill any water so that we don't throw off our calculations. That's really what they're looking for. They're not looking for, be more careful and be careful of slippage and stuff. So, I'm going to stop the video there because that's become quite a beast. I know that this isn't as neat as you're going to do on the day. I'm just focused on making sure you understand what I'm explaining, okay? If you need any more guidance on it, I'm more than happy to provide. Okay, so I'm going to stop it there.